Let's take up the next question. In Young's double-slit experiment, the wavelength of incident light is 6200 angstrom. The two slits are separated by a distance of 1 millimeter. Distance between the slits and the screen is 1 meter. Then the distance between fourth dark and seventh bright fringe on the same side of the central bright fringe is options A 1.55 millimeter, B 15.5 millimeter, C 2.17 millimeter, and D 21.7 millimeter. Now this is the problem based on the distance between the fringes. Let's write out the data first. The wavelength of the incident light is 6200 angstrom, which can be written as 6.2 into 10 power minus 7 meter. The slit separation is given to be 1 millimeter. Distance of the screen from the slits is 1 meter. And we are supposed to find out some distance, that is the distance between on the same side of the central bright fringe. Now if this is the central bright fringe, you can say that this is some fourth dark, and somewhere here we have seventh bright, and let's find out the distance between this fourth dark and seventh bright. So in order to do so, we'll have to find out the distance of the fourth dark from the center, then find distance of seventh bright from the center, then take the difference between those two distances. Let's find out the distance of fourth dark first. So distance of a dark fringe from the center is given by xn is equal to 2n plus 1 beta by 2, where beta is fringe width. Now for fourth dark, n has to be taken as 3. So when you substitute 3 here in this formula, you get 6 plus 1, that is 7 beta by 2 is the distance of fourth dark. x4 is equal to 7 beta by 2. Then the distance of bright from the center is given by distance of any bright fringe from the center can be calculated using the formula xn is equal to n beta. For seventh bright, n is equal to 7 itself. Students should be aware of this difference. For bright fringes, the value of n is the fringe number itself. Say for example, for 7th bright n is 7, for 5th bright n is 5, whereas for dark this number slightly gets changed. For 3rd dark the value of n is 2, for 5th dark the value of n is 4, for 10th dark value of n is 9, so on. That is true when you use the formula xn is equal to 2n plus 1 beta by 2 for distance. But when you make use of another formula, which is the distance of dark, which is given by xn is equal to 2n minus 1 beta by 2, then you need not make these adjustments. That is, for 3rd dark you can take n as 3, for 4th dark n as 4, and so on. But here I have considered the formula xn is equal to 2n plus 1 beta by 2, therefore I'll have to make these adjustments. Now, for 7th bright, you can call the distance as x7, which is 7 beta. Now, the gap between these two is, the distance between these two fringes is x is equal to x7 minus x4, which is 7 beta minus 7 beta by 2, which is obviously 7 beta by 2. Now we'll have to substitute for beta, which can be done using lambda capital D divided by small d. So x is equal to 7 lambda d divided by 2d. Now let's substitute the values here. X is equal to 7 into lambda is 6.2 into 10 power minus 7. The wavelength of light into the distance of the screen is 1 meter divided by 2 times small d is the slit width, it is 1 millimeter. So you can cancel this 2 by this 6.2, which is 3.1 times. So you can multiply 3.1 to 7, which is 21.7. So it is 21.7 into 10 power minus 4 meter, which can be written as 2.17 millimeter. Therefore, option C is the correct answer. Now let's go to the next question. In Young's double-slit experiment, the slits are 0.5 millimeter apart and interference is observed on a screen placed at a distance of 100 centimeter from the slits. It is found that the ninth bright fringe is at a distance of 9 millimeter from the second dark fringe from the center of the fringe pattern. What is the wavelength of the light used? Options: A. 2000 angstrom, B. 4000 angstrom, C. 6000 angstrom, and D. 8000 angstrom. Let's write down the datas first. The slits are separated by a distance of 0.5 millimeter, which can be written as 5 into 10 power minus 4 meter. Interference is observed at a screen which is at a distance of 100 centimeter, is nothing but 1 meter. It is found that the ninth bright fringe is at a distance of 9 millimeter. That is, some distance is given between two fringes and that distance is 9 millimeter. Now to find the wavelength of light. So let's understand what is that distance given in the problem. If you consider this as the screen, then if I call this as the center of the screen O, then let this be the second dark fringe, which I'll write as 2D, and let this be the ninth bright fringe, which is written as 9B. The distance between these two fringes is written as X. Using this, we are supposed to find out the wavelength of the light used. Okay, in order to solve this, you need to know the distance of nth bright fringe and nth dark fringe from the center of the fringe pattern. So let's take up the bright first. Distance of nth bright is distance of nth bright from the center of the fringe pattern is always given by xn is equal to n beta, where beta is the fringe width, which is equal to lambda d by d. Now distance of ninth bright, for ninth bright, you need to know that for bright, n is equal to the number of the fringe itself, that is the order of the fringe. Here for ninth bright, n is 9, therefore the distance x is just 9 beta. Let me call this as x1, since I have considered bright and now I'll have to consider dark, which will be given the symbol x2. Now let's go to the dark fringe. Distance of nth dark is given by the formula xn is equal to 2n plus 1 beta by 2. You can use this formula. When you use this formula, n starts from 0, 1, 2, 3, 4, so on. So now for second dark, the value of n should be taken as 1 and not 2. This is because of the formula that we have considered. If you take xn is equal to 2n minus 1 beta by 2, then for second dark you can take n is equal to 2. Students should be aware of this difference. When you stick on to the formula 2n plus 1 into beta by 2, the value of n should be chosen carefully. Now for second dark, n is taken to be 1. Now substituting, we get, let me call it as x2, since the distance of bright is taken as x1, the distance of dark is taken to be x2, which is 3 beta by 2. on substituting 1 in place of n. Now, what is the gap between these two fringes? One is at a distance 9 beta from the center, the other one is at a distance of 3 beta by 2 from the center. In order to know the separation between these two, you can call it as either delta x or simply x, which is the distance between them, which is written as x1 minus x2. So this is 9 beta minus 3 beta by 2. So by taking beta common here, 9 minus 3 by 2 times what is beta is lambda into capital D divided by small d. Therefore, 9 minus 3 by 2 is 15 by 2. 15 by 2 into lambda into capital D divided by small d is equal to x. Now, let's rearrange the terms to get an expression for lambda wavelength. Lambda is equal to 2dx divided by 15 into capital D. Now let's substitute the known values. Lambda is equal to 2 into small d is 5 into 10 power minus 4 into x is 9 into 10 power minus 3 divided by 15 times capital D is just 1 in meter. You can simplify this. This goes 3 times. And again, this can be cancelled with this 9. So we are left with 6 in numerator along with 10 power minus 7. It has to be in meter. Therefore, lambda is 6 into 10 power minus 7 meter. In angstrom units, you can write it as 6000 angstrom. Therefore, option C is the correct answer. Now let's take up an important question, dear students. In an Young's double-slit experiment, the fringes are displaced by a distance x when a glass plate of refractive index 1.5 is introduced in the path of one of the beams. When this plate is replaced by another plate of same thickness, the shift of fringes is 7 by 5 times x. Refractive index of the second plate is options A 2.0, B 1.75, C 1.7 and D 1.2. Dear students, in order to solve this problem, we must be aware of an expression of the shift produced when a glass plate is placed in the path of one of the interfering beams, and that shift is given by the expression x is equal to d by d into mu minus 1 into t. Here mu is the refractive index of the material of the glass which is placed in front of one of the slits, and t is its thickness. Since the fringe width beta is nothing but lambda into d by d, you can write d by d equal to beta by lambda. Therefore, the expression for shift becomes x is equal to beta by lambda into mu minus 1 into t. Now there are two cases explained in the problem. In the first case, when the refractive index is 1.5, the shift produced is x. Then in the second case, when the refractive index is unknown, the shift produced is 7 by 5 times x. So let me write down the expression for both the cases. In the first case, the shift produced is x, which is beta by lambda times mu minus 1 into t. And in the second case, let me call this as equation 1, and in the second case, the shift produced is 7 by 5 times x. That should be equal to, remember, beta remains the same. That is, when you place glass plate in front of one of the two slits, fringe width doesn't get altered. What change you can see is that the entire fringe pattern gets shifted. So the direction of the shift is same as, or the direction of the shift depends on the position of the glass plate. Or in other words, when you place the glass plate in front of the upper slit, the fringe pattern gets shifted upwards. Otherwise, when you place the glass plate in the downward slit in front of the downward slit, then the entire shift takes place downwards. So the second case, the shift is 7 by 5 times x, that should be equal to beta, which remains the same, and you have not changed the source of light, therefore the wavelength lambda remains the same, but the refractive index is, which is new thing, which is unknown, therefore it is written as mu dash minus 1 into t. Here it is mentioned that the thickness is same, therefore I have made use the same expression t. Now when you take the ratio, let me take 2 divided by 1. So in LHS you are left with 7 by 5 is equal to beta by lambda gets cancelled, mu dash minus 1 divided by mu minus 1. Or mu dash minus 1 is equal to 7 by 5 times mu minus 1. So this is equal to 7 by 5 times, what is mu minus 2? Initially it was 1.5 and 1.5 minus 1 is 0.5. So this is equal to 7 into 0.1, that is 0.7. So mu dash is equal to 1 plus 0.7, mu dash is equal to 1.7, therefore option C is the correct answer. Now let's work out one more problem. In double-slit experiment, when a glass plate of refractive index 1.5 and thickness t is introduced in the path of one of the interfering beams of wavelength lambda, the intensity at the position of central maximum remains unchanged. The minimum thickness of the glass plate must be options A. Lambda, B. Lambda by 3, C. 2 lambda by 3, and D. 2 lambda. Dear students, again this problem is based on the shift produced when a glass plate is placed in front of one of the slits, and the expression for the shift is given by x is equal to beta by lambda into mu minus 1 into t, where mu is the refractive index of the glass. Okay, here in this problem it is mentioned that when the shift happens, the intensity at the central maximum remains unchanged. It means that the central fringe pattern is occupied by one more bright fringe itself, because when bright fringe is not replaced by bright fringe, the intensity must change. In order to maintain the same intensity at the center of the screen, however, shift must take place. In order to support shift and also to maintain the same intensity, it is evident that the central bright fringe should be occupied by another bright fringe, such as the first bright fringe or the second bright fringe or the third bright fringe, so on. Or in other words, it is clearly mentioned that the shift must be the integral multiples of fringe width. But you need to get minimum thickness of the glass plate. That is the condition mentioned here. You can directly equate these two, stating that n beta is equal to beta by lambda into mu minus 1 into t. Here n indicates the number of the fringes or the order of the fringe. But for minimum thickness, the number of fringes should be 1, which means that the first bright fringe should occupy the position of the central bright fringe. So therefore n is equal to 1. So that makes beta is equal to beta by lambda into mu minus 1 into t. So you can cancel beta here, which gives you an expression for thickness that is equal to lambda divided by mu minus 1. However, the value of mu, that is the refractive index, is given to be 1.5. Therefore, t is equal to lambda divided by 1.5 minus 1, that is lambda by 0.5, that is equal to 2 lambda. Therefore, the thickness, minimum thickness of the glass plate should be 2 lambda. In this case, the shift takes place in such a way that the first bright fringe will occupy the position of the central maximum so that the intensity at the central maximum remains unchanged. Therefore, the correct answer is option D, 2 lambda.